We learned that there are two important problems of exact linearization, that is full state linearization and input output linearization. We have already talked about full state linearization, the case when relative degree is equal to n, that is particularly important, and we see that if we have this nonlinear system with relative degree to be equal to n, then for the purpose of full state linearization we had defined this state transformation diffeomorphism, which converted this nonlinear system into this normal form, and where AC, BC and CC, these are given by these matrices, and then after using appropriate control law, we converted this nonlinear system into this particular form. So what we see is that this system is both full state linearized as well as input output linearized. All the state equations are linear state equations, and furthermore relationship between newly defined input variable v and the output variable, this relation is a linear relation. You can even find a transfer function between this new input and the output. So if relative degree is equal to n, then the situation is simpler. This state transformation will not only give you full state linearization, but it will also give you input output linearization. The example that we studied in our previous lectures is that of a magnetic suspension system. We learned that we had this nonlinear system with the output equation y is equal to x1, and this system had relative degree equal to 3, and we had defined this particular state transformation. This transformed this nonlinear system into this particular format, and then by defining appropriate control law we had converted this nonlinear system into this particular form. So both it is full state linearized as well as input output linearized. So this situation when rho is equal to n, that is quite clear. We can easily obtain input output linearization. To talk about the situation when a relative degree is less than n, we again consider this nonlinear system described by these state equations and the output equation, and we take this case relative degree less than n, and if relative degree is less than n, we can utilize this state transformation where h of x is this over here, and we have already learned how to compute the Lie derivatives of h of x along some function f of x. So h of x, its Lie derivative along f of x and up to its rho minus first Lie derivative along f of x. Here these phi 1 of x, phi 2 of x up to phi n minus rho of x, these are some functions of state variables, and these are selected. You have choice to select these functions. These are selected such that t of x is a diffeomorphism. We have already learnt what is a diffeomorphism. Diffeomorphism is a state transformation for which the inverse transformation exists, and both the state transformation and its inverse transformation both are smooth. So these phi i's are selected such that this state transformation is a diffeomorphism, and there is a theorem in the book by Hassan Khalil which states that such functions do exist, at least locally. So if relative degree is less than n, such functions always exist, which will make this transformation to be a diffeomorphism. Now how to find these functions, that will be discussed. In addition to making this thing to be a diffeomorphism, these phi i's must satisfy this additional condition, that is partial derivative of phi I with respect to x multiplied by g of x, this must be 0 for all I between 1 up to n minus rho. Here we see that from here to here, this is a vector function of x. We give it some name, psi of x, and this part we call it phi of x. And we also define this vector by a new symbol eta, and this vector by a symbol xi. That is, this z, this new state vector z is split into two parts, eta and xi. What is dimension of xi? So from here h of x up to this rho minus first Lie derivative. So here these are rho elements. So zeta is rho by one dimensional vector, and what is eta? N minus rho dimensional vector. And overall this vector has the same dimension as this new state vector z. That is, the dimension of this vector is n. And this state transformation will transform this nonlinear system into this particular format. Eta dot is equal to some new nonlinear function of these new state variables eta and xi, and xi dot is given by this relation. The output equation is equal to y is equal to cc into xi, and we shall prove that this state transformation converts this nonlinear system into this form, where these nonlinear functions are given over here. We shall also derive these expressions, and once we have this form, which we call the regular form or normal form, we can define this control law as we did for the case of full state linearization, and then this system is converted into this form, which is input output linearized system. The new input is v and output is y. So this part of the system is input output. We see that input output relation is a linear relation. You can even find a transfer function between this input and the output. There are some additional state variables, and these state variables do not appear in this equation as well as in this equation. These state equations are called internal dynamics, and these internal dynamics are unobservable from output because these state variables do not have any effect on the output equation. So these equations are called internal dynamics, and once we have this kind of input output linearized system, we can solve the tracking problem for this nonlinear system. This is basically linear system. We can solve the tracking problem for this linear system, which will be basically the tracking problem for this nonlinear system. So is this clear? In addition to solving the tracking problem, we must also ensure that these internal dynamics are also stable. So we shall talk about these internal dynamics, stability of internal dynamics in much more details in some later lectures. First we want to prove this thing, that is, this state transformation will transform this nonlinear system into this normal form. We want to prove it. So the proof of this statement is simple. Relative degree equal to rho. What is its meaning? We have defined relative degree, and if relative degree is equal to rho, then this Lie derivative is equal to 0 for I equal to 1 to up to rho minus 1, and this Lie derivative is non-zero. This is the from the definition of relative degree. And here eta is equal to phi of x. Therefore eta dot is equal to the derivative of this phi with respect to x, and then derivative of x with respect to time. And x dot from system equations is given over here, and you see that partial phi over partial x multiplied by g. This partial phi over partial x multiplied by g, this is equal to 0. Why? Because we have selected phi in such way. We have selected phi to satisfy this condition. Therefore, this part is equal to 0, and which is equal to partial phi over partial x multiplied by f of x. So this phi is some function of x, its partial derivative will be some function of x, and this is also function of x. So their product will be some another function of some another function of x, and we call that function to be equal to f naught. And then x, this state variable x, that is somehow related with new state variables eta and xi, and we can just replace x with the new state variables to get this function. So we have proved this first part, and we want to prove the second part. What is xi I? This xi is vector, so its ith element. What is that? What is xi I? Xi I is the ith component of this vector, and therefore xi I dot is equal to the partial derivative of psi I with respect to x, and then derivative of x with respect to time, where x dot is given over here. Furthermore, what we see is that psi I, what is psi I? From here you see that psi 1 is equal to h, and its ith component will be equal to I minus first Lie derivative of h along f of x, and its partial derivative of psi I with respect to x, that is written over here. Rest of the term is the same, and this is equal to this term multiplied by f of x, that is nothing but the ith Lie derivative of h along f of x. And what is this term multiplied by this thing? This is Lg Lf I minus 1 h, and u is this u. So we see that from the definition of relative degree, for I from 1 up to rho minus 1, this thing is equal to 0. This thing is equal to 0 for I starting from 1 up to rho minus 1. This term is 0. Therefore, for this I between 1 and rho minus 1, zeta I dot is equal to Lf I h. What is this Lf I h? What is that equal to? So this is psi I plus 1. So this thing will be equal to psi I plus 1, which will be equal to xi I plus 1. So this is psi I plus 1, and which is by definition equal to xi I plus 1. So for I between 1 and rho minus 1, this is the case, and when I is equal to rho, then again we have written the same equation, except that instead of I we have substituted it to be equal to rho, and for that case you have this situation, which is this expression. And now this term, since relative degree is equal to rho, so this term is now non-zero. This term is non-zero, and if you take this term common from this expression as well as from this expression, we are left with u over here, that is written here, and this term divided by this expression which we have taken common. So we have this equation, eta dot is equal to f naught of eta zeta, and for I between 1 and rho minus 1, we have zeta I equal to zeta I plus 1, and for I equal to rho we have this situation. Here it should also be less than or equal to. Here is equality sign is missing by mistake. So if we call this thing to be gamma of x and this one to be minus alpha of x, then these equations which we have written over here, rewritten here, zeta 1 dot is equal to zeta 2, this zeta 1 dot is equal to zeta 2, and zeta 2 dot equal to zeta 3, and zeta not zeta xi rho minus 1 dot is equal to xi rho, and xi rho dot is equal to gamma of x u minus alpha of x. That is this particular form. Hence we have proved that we have demonstrated that this state transformation will transform this nonlinear system into this particular form. This general discussion is always a little bit difficult. However, if we apply it to some particular example, the situation becomes much more clear and simpler. Let's demonstrate it with one simple example. We have this nonlinear system given over here, and what is relative degree that can be easily computed. Y dot is equal to x3 dot equal to theta x1 x2. So the control input is not appearing over here. We need to take the second derivative, and in the second derivative we see that x1 dot appears, and x1 dot is basically given over here, and we see that the control input appears in the expression for y double dot. Therefore rho is equal to 2, not in the entire state space, rather in the domain defined by this set, that is x2. You see x2 is being multiplied with u, so if x2 is not equal to 0, only then this u will appear in this equation. And now from this statement over here, we take this state transformation. Relative degree is equal to 2, so we start with h of x, go up to relative degree rho minus 1, so we should start from h of x and LF h of x. So here h of x, LF h of x, and phi 1 we have to select phi 1. H of x is already given over here. We already know how to find this Lie derivative. That is simpler. Lie derivative of h along f of x is given by definition over here. It's a partial derivative of h with respect to x. Only x3 is here, so its partial derivative with respect to x1 with respect to x2 is 0, and with respect to x3 it is 1. And here is f of x, so this Lie derivative comes out to be equal to theta x1 x2. So h of x is x3, this Lie derivative is given over here, and we have to find phi 1 of x. How to find this phi 1 of x? Phi 1 of x has to be selected such that this t of x is a diffeomorphism, and furthermore this condition is also satisfied. So let's check this condition. Partial phi 1 over partial x multiplied by g, that must be equal to 0. So what I have not written the partial derivative of phi 1 with respect to x2 and with respect to x3, because whatever is over here multiplied with 0 will become 0. So that is given over here. Partial phi 1 over partial x1, this must be equal to 0. So what is its meaning? This phi 1, right. So phi 1 should not be a function of x1. We can take phi 1 to be any function of x, but it should not be function of x1. Let's take this to be equal to x2. Simpler. You could have even taken complex function of x2 and x3, but we have taken some simple function. And remember that this is not the only choice for phi 1. You could have taken some other function. It can be function of x2, it can be function of x3. So always take it as simple as possible. For example, I have taken it to be x2. You can also take it to be equal to x2 square. You can also take it to be x2 square plus x3 and something different as well. What if I take phi 1 to be equal to x3? This is also a function of x and not function of x1. So what if we take phi 1 to be equal to x3? In that case, this will not be a diffeomorphism. What is meaning of diffeomorphism? Inverse transformation must exist. So if I take phi 1 to be equal to x3, then it will not be a diffeomorphism. Inverse transformation will not exist. Likewise, if I take phi 1 to be equal to 0 or some constant, again it will not be a diffeomorphism. So it must be a diffeomorphism. We can verify that this particular choice is a correct choice because this state transformation will be a diffeomorphism. Again we define similar new variables xi1, xi2 and eta, and we find the inverse transformation, and we see that inverse transformation exists. From here x2 is equal to eta, so x2 is equal to eta, x3 is equal to xi1, x3 is equal to xi1, and x1 is found from this expression. So we see that inverse transformation exists, and both this transformation and inverse transformation are smooth, their derivatives are existing. So once we have this state transformation, then rest of the task is very easy. We can simply take eta dot is equal to x2 dot from here, and x2 dot is given by this expression, and this is after substitution of x2, x1 and x3 by these newly defined variables, we have this function which is some another function of eta and xi written over here, this first equation. And now xi1 is equal to x3, therefore xi1 dot is equal to x3 dot, and x3 dot is given from this equation theta x1 x2, and this theta x1 x2 is by definition equal to xi2, and xi2 dot is given from here, and after substitution of these derivatives we have this equation which can be rearranged to write it in this particular form. Xi2 dot is equal to this expression, and here from here you can define the control law. This is in this particular form. Where is that? This particular form, and you can define control law to obtain linearization. The output equation y is equal to x3 and x3 is equal to xi1, so y is equal to xi1. The same equation rewritten over here, and this particular form is called normal form. These dynamics written over here, these are called internal dynamics. We can solve the tracking problem for this this system, but we have also to ensure the stability of internal dynamics. We shall talk about stability of internal dynamics in the next lecture. And the control law is obvious. It can be taken, this control law, to cancel these nonlinearities. We have this control law. This control law will transform this normal form into this particular form, which is input output linearized form. Here there is one more observation. We have taken this control law to cancel out all these terms, but we can also somehow take a slightly different control law, for example this one as well. And जी नींद आ रही है तो ये आरफाना कलाम है, इसमें नींद तो आती है. नॉन लीनियर कंट्रोल इतनी बड़ी बड़ी इक्वेशंस देखेंगे तो फिर तो नींद आएगी। तो चलें बहरहाल क्या क्या किया जा सकता है, ये है यार फाना कलाम ना। तो so over here this is u which is different from this one. What is advantage of this new u? So you see that some of nonlinear terms have not been cancelled. For example, we have not I think we have not cancelled which term? This term x1 multiplied by x2 and this term x1 multiplied by x2. We have not cancelled these two terms. Why we have not cancelled these two terms? Because when this thing is substituted with a new state variable xi, that will be linear term. And with this control law, you see that this control law is simpler compared to this control law, and the terms which have not been cancelled, those are not creating problem because those terms are linear terms. And anyway, you can take this control law or this control law, whichever you like, but this is simpler and therefore maybe better than this one. So you have this linear system and input output linearized system, and tracking problem can be solved for this linear system. And simple control is state feedback control if you only want to solve the stabilization problem, and however you have to ensure the stability of internal dynamics as well. So this is brief discussion on input output linearization. We have learned how to achieve input output linearization. There is one very important point that is in addition to ensuring the stability of these dynamics, we have to ensure the stability of internal dynamics as well. And in the next lecture we shall talk about stability of internal dynamics, inshallah.